Hey everybody, let's take a look at Chapter 5, Properties of the Envelope. This video will explore thermal properties of materials and thermal capacity. We have two examples, an igloo and an adobe dwelling, both in opposite extreme climates. The igloo, as you can see, my inside air is roughly 20 to 30 degrees, and the outside air negative 30 to negative 40 degrees. And if you take a close look at this, the curves, as this is plotted out throughout the day, somewhat are parallel to each other. You can see that they raise and dip about the same time during the day. Where in the adobe dwelling, the inside air, it remains somewhat consistent between 70 and 80 degrees. But take a look at the roof surface temperature at approximately 4 p.m. in the afternoon. It peaks out at 140 degrees, and that energy is then stored in the thermal mass of the building, and it really does not release until later on in the evening. So as the outside air temperature gets cooler, the energy or the heat that's stored up in the mass of the adobe structure is released in the evening. These are all factors that affect energy conserving building design. The focus of this chapter is on elements of energy conserving building envelope design. Because thermal properties of materials and assemblies are related to energy flow through them, an understanding of the units of measurement of energy is necessary. In the SI system of units, energy is measured in joules, and the rate of energy flow through a material is measured in joules per second, which is called watts. Both joules and watts are small units. Therefore, kilojoules and kilowatts are commonly used. In the US system of units, the unit for energy is British Thermal Unit, or BTU, and the corresponding unit for rate of energy flow is BTU per hour. Heat, or energy, always flows from the object at higher temperature to the object at a lower temperature. So, let's take a look at how energy transfers through common building materials. Conduction is the phenomenon of heat transfer between the molecules of a substance that are in contact with each other. Convection occurs only in fluids, gases or liquids, and may be described as energy transfer by actual bulk motion of a gas, such as air. Radiation is a transfer of energy between two objects in the form of electromagnetic waves. Thus, the heat and light received from the sun, from a burning candle, or from an electric lamp reach us by electromagnetic radiation. A new vocabulary word, simultaneity, page 112 in your text. Simultaneity is conduction, convection, and radiation acting together when energy is transferred through building components. During the process of heat transfer through a building envelope, that's the outside skin of the building, all three modes usually come into play simultaneously. Thus, to reduce heat transfer through the envelope, All three modes must be considered, and the heat transfer potential of each mode must be reduced. The outside of a building absorbs solar radiation from the sun, and once that outside material, in this case it would be a brick wall, absorbs that energy conducts through the material into an airspace. In that airspace, that energy convects, and also we have radiation from the outside skin or brick wall, and that energy conducts through the inner face of the wall, which is also brick. Then that energy is released on the inside through convection or radiation. To understand the rate at which that energy transfers through the building envelope, we first have to understand what R value is and how it relates to each different building component. R value is the measure of the ability of a material to resist the flow of heat through it, where P is a constant property of the material representing the ability of the material to resist the flow of heat through it. It's important to note again that the P value is a property of the material, whereas R value is a property of the component of a certain thickness. Because they are related to each other by the relationship of R equals PL, where R is resistance, P is the value of the property, and L is the length or the thickness of the component. P is the R value of 1 inch of that material. So let's take a look at a typical R11 3.5 inch thick bat of fiberglass insulation. So this is R11, so it's R11 insulation, and so it's, if I took the thickness of it and multiplied it by the P value, I would come up with the R value. So in this case, my 3.5, which is roughly what the P value is, times 3.5 gives us an R11 value. Another common building material is polystyrene insulation in a board form. In this case, we can see that it's an R3, and it's also a 1/2 inch thick. So if it's a 1/2 inch thick and I double that to make it an inch thick, then I'd have to also double the R value. So the P of this extruded polystyrene insulation would actually be an R6. So another example, if the P value of concrete is 0.15, and you can find that, and for other common materials, on table 5.2, and table 5.2 is on page 114 of your text. So if we want to know what the R value of a 6-inch thick concrete wall is, we would take the P value and multiply it by the thickness, and that would give us the R value of that component. In this case, the R value is 0.15 times 6, which is 0.9. The R value of a 6-inch thick concrete wall is less than R1. But in this case, we would round it up. We'd round the 0.9 to R1. So the P value of fiberglass insulation is 3.5 from table 5.2. What is the R value of a 6-inch thick blanket of fiberglass insulation. So to find the R value of a 6-inch thick blanket of fiberglass insulation, I would go to the table and I'd find the P value of that fiberglass insulation, which is 3.5, and I'd multiply it by 6. So 3.5 times 6 is equal to 21. So to figure out the rate of heat transfer by conduction, or QC, we would first have to take a look at, we'd have to measure the temperature of both sides of the material. So QC is equal to T2 minus T1. And again, we would need to know what the direction of heat conduction is. So my heat is transferring from face T2 to face T1. So T2 minus T1, and that would have to be divided by the R value, which is P times L. There are other factors that influence thermal resistance. For example, if we take a look at page 114 in your text, the top of the column, metals. Metals are very dense materials, very heavy, dense. So their P values are actually extremely low. So steel is 0.0032. And we get into ceramic materials like clay brick, and the P value for clay brick, it's much higher than metal. So that's 0.2. Wood-based materials are even higher. So a solid piece of lumber with 12% moisture content has a P value of 1.2, so we get even higher. And then we get into the insulating materials. So let's see here. Fiberglass bats are 3.5 per inch. Silica aerogel blankets are 10. It's 10 per inch. And then once we get into the gases, so like air actually has a P value of 5.6, argon's 8.9, krypton is 15, and water actually is 0.24. So water is going to be much less than the other gases. So in looking at two different types of rigid board insulation, the first being expanded polystyrene, or EPS, is also called beadboard. So expanded polystyrene is little beads that contain air, whereas closed cell polystyrene, or XPS, or polyisocyanurate, ISO, those cells contain gas. So the HCFC gas is going to have a higher R value than, let's just say, air. So the difference here, based on page 114, table 5.2, the HCFC gas has a P value of 15, where air has 5.6. So obviously the HCFC gas is going to be a better insulator. This is the end of Chapter 5, Part 1. I wanted to encourage you to go ahead at this point and take the quiz on Chapter 5, Part A now.